all the peripherals are connected to the CPU through this bus. Okay. So, basically for this bus there will be a bus master, or what we call as bus control logic. So, if I want to access the bus as a CPU, I basically give a request to the bus control logic, then the bus control logic will resolve of all the requests, it will grant. If you make a request, it will grant you the request. That means you become the master of the bus, and there will be somebody who is receiving, that will be the slave of the bus. Or you could have multiple slaves if you are trying to send data to multiple units, right. So, the bus plays a very crucial part, as we see when we move from, this is a single core description. When we move from a single core to multi-core description, the bus becomes much and much complex. So, lot of activities will happen over the bus. Okay. So, this is a structure of a simple processor. Any doubt in that? Okay. Now, let us look at this read after write. I am writing into R2. The first load instruction is writing into R2, 1 minute. The first instruction is writing into R2, the second instruction is reading from R2. So, this is a read after write, right. So, what does the first instruction do? It will takes from the memory address, let R1 be some 1000, so from 1020 it will take some value, let it be some value, let us call that value as 10. It will read this 10 and it will store it in the register file. This is what the load does. And what will add do? It will read from the register file and perform the addition and then store back to the register file. So, the load instruction takes the value from 1020, assuming R1 is storing 1000, it takes the value from 1020, let me say it is 10, and then stores it in R2. The next instruction that is following it, right, will read from R2 and it will do the addition here and write back the result onto R3, right. So, the data in the first instruction is actually moving from the memory through the CPU to the register file, and in the next instruction it is basically taken from the register file and operated upon, and the results are stored back in the register file. So, for this data 10, it goes to the register file and then it goes to the register file through the CPU and then comes back to the CPU for next processing. When load when load is in the store result stage, when load is actually storing the result in R2, add will be waiting in where? In the data fetch stage, correct, because it needs the value of R2 to go and do the next step. So, it has to wait. How it is going to wait we will see, but the hardware will make it wait in the data fetch stage, while load is in the store result stage, the add will be waiting in the data fetch stage, correct. Now, where is this, where is the data fetch stage? Inside the CPU, right, the pipeline is inside the CPU. So, somewhere load is there here while add is waiting here, correct. Now, why should, so the question now is, why should result of LD load go to R2 in the register file and then come back to the ALU? In its way from the memory to the register file, can't I take the value and keep it? Why should I spend extra time for it to go to R2 and then again fetch back from this? When 10 is moving from the memory to the register file through the ALU, I can just basically take a copy of this and give it to add, can't I? Right? Right? And this particular concept is called operand forwarding. So, when I am taking the value of R2 and I am going to store in the register file. Of course, it has to go to the register file. In that path, since it is going through the ALU, I can basically also take that copy of that value and give it to add. Are you able to follow? So, very quickly I will tell you again, there is a load instruction which is reading from 1020 and loading into R2. There is an add instruction that immediately follows it, which uses the value of R2. So, in our pipeline, this add instruction should be waiting inside the CPU in the data fetch stage, while load is completing its operation. In the store stage of load, what it should do? It should take the value in 1020, namely 10, and it will be storing it in R2, and that movement is through the ALU, right. In the last semester, when you actually did the hardware, how did the move instruction work? It came through the ALU and went to the register file. Do you remember still when you constructed this, right? When I want to initialize some value, it actually moved through the ALU, it did not go. So, it came to the CPU and then moved. The instruction comes to the CPU, right, and then you move it inside. Okay. So, the point is, when the data is going to the register file, I can just take that copy of the data and then I can forward it to the waiting instruction, rather than I writing in register file and asking this add to go and access the register file and take it. There are two important things that we save here. One thing is, accessing the register file also takes some amount of time. The second thing is, this store has to load has to complete, the load has to complete writing into R2 before I start. So, there is again some more time elapsed in that, right. So, these two time intervals are shortened by just doing this forwarding. So, this is the simple easy way of understanding operand forwarding. Okay. Are you able to appreciate, right? Okay. Now, we will do this entire stuff here. So, you all understood register renaming, you all understood operand forwarding. Now, we will do something called register renaming, right. Now, let us take these instructions. So, there were three hazards that we have been talking of: the raw, the var and wav. Now, what we did in the previous slide was how to handle a read after write, and in the read after write, of course, the add will be waiting, but it will not wait for too long. We will try and shorten its waiting period by doing operand forwarding, but the add, the subsequent instruction has to wait for the data to complete. That is why we call it as a true dependency, right. I can't do any jugglery and get away with it. On the other hand, let us look at the other two type of data dependencies, namely write after read and write after write, right. Okay. Now, let us take this set of 6 instructions: add R1, R2, R3, store the result of R1 in R4 plus 50, add R1, R5, R6, subtract R7, R1, R8, store the result of R1 in R4 plus 54, add R1, R9, R10, correct. Now, what are all the read after write? There is a read after write between 1 and 2, because 1 is writing into R1, store is reading from R1 and storing it in R4 plus R50, correct. So, there is a read after write, there is store is reading from R1 and storing it in R4 plus R50. So, this is a read after a write. Similarly, 1 and 4, there is a read after write, this is writing and this is reading, and there is 1 and 5, there is a read after write. 3 and 4, there is a read after write, this is writing and this is reading. 3 and 5, there is a read after write, okay, this is writing and this is reading, the read after write. So many dependencies are there between for R1 within these 5 instructions, okay. Now, let us take write after read. What are write after read? Between 2 and 3, there is a write after read, because this is writing and this is reading. Store reads from R1 and stores in R4 plus 50, while add writes into R1 the sum of R5 plus R6. between 2 and 6 there is a write after read, right. This is writing and this is 2 and 6. So, this is reading and this is writing. So, write after read. Between 4 and 6 this is reading and this is writing, and 5 and 6 this is reading and this is writing, right. So, so many dependencies we are seeing between this. And write after write, that you see between 1 and 3, this is writing to R1, this is also writing to R1, and 1 and 6 write after write, and 3 and 6. So, so many dependencies are there between these 6 instructions. Of course, it is a cooked out example, but we can get such examples, okay, right. Now, why are these actually again I repeat, why are these dependencies extremely important? Because any of these instructions can execute in any order. We want Rajinikanth here, right, superscalar. So, I can allow every instruction can work out of order. So, if I am free, for example, R2 can be an output of some floating point division integer casting. So, that floating point division will be taking so much of time. So, this add has to wait for that. So, this store also will be waiting for R1 to complete, correct, because R2 somewhere here would be doing lot of floating point operation. But so this add cannot proceed till that R2 completes. But note here, this add and this subtract can go on, because R5, R6, R7, R8 they are all free. You are getting this, right. So, these two will start executing even before these two, because this is waiting for something and these two are independent of this, and that floating point division can be, it will may land up with a floating point exception, okay, right. So, it can go on forever while this fellow can start doing something else. So, all these 4 instructions can execute even before this fellow touches, right. Are you getting what I am trying to say, right. So, and these type of things have to be enabled so that you get that superscalar behavior, CPI is less than 1, right. So, because of out of order, if I am allowing 3 and 4 to execute before 1 and 2, all these hazards become extremely relevant, correct, okay, right, because if 1 and 2 are the fellows who are going to finish last, the value of R1 would be the one that is output by this add instruction rather than this add instruction, right, and that I have to somehow handle it. When at this point when I observe what should be the value of R1, I should get the value of R1 that is output by instruction number 6 and not instruction number 1, correct. But at the same time I would love to allow 3, 4, 5, 6 to execute before 1 and 2 actually starts executing, to actually save time and get my cycle per instruction less than 1. Are you able to follow what I am trying to say, right. So, in this context all these 3 dependencies become extremely crucial. Now, raw, we can't do anything about raw, the only thing we can do is operand forwarding that I have explained in the previous slide. Now, what can we do about var and wav, okay. Let us see this. Suppose I go and replace, please note that the life of R1 starts at 1 and ends at 3, because at 3 R1 is again rewritten with a new value, right. We have done that liveliness analysis, still you remember the interval graph, please remember that, okay. So, the life of R1 starts at 1 and it stops at 3. The life of again R1 starts at 3 and ends at 5, because 6 again somebody is writing into R1. So, what I am doing is, for the other avatars of R1, other lives of R1, I will go and replace it with some other value. For example, what I have done is, these R1s I replace it with R12, okay. Are you following what I am saying? These R1s I replaced it with R12. Now, where are the var and wav? Everything went off. Program is correct, whatever this program is going to achieve is exactly what this program is going to achieve, Functionally both are equivalent. When I replace this R1 with R12, all your var, vav, all these hazards that were there, sorry, this var and vav completely gone except for the 6. So the only var and vav are now between 2 and 6, between 2 and 6 and 1 and 6 and 2 and 6. Now this is very far off, 6 is very much far away from 1, 2. So by the time you reach 6, right, by the time you reach 6, these instructions would have been completed, we expect it to complete. So this will not hinder this, var or vav will not hinder that. Okay. So by doing register renaming, what I have done, I have renamed the register. From R1 I just replaced it by R12. By doing that, and how did I replace by R12? I took all the instance of R1, so I took where R1 is getting initialized, it is getting initialized at 3, and till the next initialization of R1 I go and replace all instances of R1 with some other register name, namely 3, 4 and 5 I replace R1 with R12. The moment I do that, what happens, all the var and vav that existed completely is gone. 1 minute. And after doing that, there is only one more var or vav, that is between 1 and 6 and 2 and 6, and now you see that this is much far away, the window where 6 will enter into the CPU is much far away from the windows of R1 and R2, so 1 and 2, instructions 1 and 2, and so I do not rename it, because by the time this fellow comes these two would have completed. Okay. So this is how we start processing the thing. Okay. This I am coming to your doubt, this register renaming can be done by the compiler. If it is done by the compiler, of course the var and vav hazards can be removed there, right, but in the case of static scheduling. But in dynamic scheduling, who should do the register renaming? The hardware should do the register renaming, and that is the thrill. Okay. How does the hardware automatically do register renaming? How does the hardware actually do operand forwarding, right? So because compiler is dumb, as I told you, it will just take the C code, it will write an assembly code and give it. Any dependency, everything is left to the hardware. Now how will hardware do it? So that is a very interesting question that we will answer. But if it is going to be software and we are going to have pipelining like this, then the register renaming can be done by the compiler. But note that this var and vav just evaporated the moment I went and renamed. So that is why we call this data dependency as a false dependency or a named dependency, right. It is all because of a name, okay, nothing more. Okay. Now we will do this, this is the the architecture, the micro architecture, which is the hardware which is going to do your dynamic scheduling, which will do operand forwarding and register renaming. The operand forwarding is to handle raw hazards, the register renaming is to basically handle the var and vav hazards. It will automatically do register renaming, your compiler is as dumb as me and the architecture is as intelligent as you. Okay. Okay. So it will do very good functions. Okay. Okay. Now chal, so how does this go, right? So there is an instruction fetch unit, it has to fetch the instruction. So what is the step, first step when we are trying to execute an instruction? Fetch the instruction. Now I want superscalar, right, so I can't fetch one instruction, so I will fetch some 10 instructions, I can fetch 4 instructions, I can fetch 2 instructions. So let us say we will fetch 2 instructions at a time or 4 instructions at a time. Now let us go back to RISC and CISC. Okay, I will not just teach this, I will teach lot of peripheral things so that you know understand this. If I go and look at CISC, right, our famous by x86 Intel Inside, what will happen? I will have instructions that are 1 byte to instructions that are 34 bytes in length, okay, arbitrary, some random number, okay, right. So if I say fetch 4 instructions, I do not know where that 4 instruction will start, where it will end, correct. So I will go and fetch some amount of bytes and pray God it is going to give me 4 instructions, okay. But in the case of RISC, what will happen? I know for sure each instruction is 16 bit. In your CST course you have seen, right? Each instruction was 16 bits. So if I bring 48 bits, I am sure 4 instructions are going to be there. So that is very important. So this type of an architecture will work extremely well when it is a RISC architecture. Okay. Now I fetch 4 instructions. Now there is something called a register status indicator, okay. One by one, please see the captions that are going. Hey, I spent a lot of time preparing this slide, so enjoy that, okay, my pain, okay. So instructions are fetched one by one and decoded to find the type of operation and the source of operations. This is in a general thing. So instructions are fetched in many, okay. So in a bunch and decoded to find the type of operation and the source of operands, right. So I will have multiple decode units inside this instruction fetch unit, okay. Now what will happen? Now there is the next thing that we need to see is, the next thing is, I have something, you all understood what is an instruction fetch unit. It will fetch many instructions and decode and find out what are the operations to be done and what are the operands. Now there is some register status indicator. What will the register status indicator do? If it is 0, so for every register there is one entry, every general purpose register, right, there is an entry. If the latest value that I want, if it is there in the register itself, then it will have 0. If the latest value I want is currently being computed by one of these execution units, then it will have the number of that execution unit. Let me repeat, for every register, every general purpose register like your EAX, EBX, like that, R1, R2 to R2, 128, for every register there will be one entry, right. That will not be just a bit, it will be an entry, right, it can be an integer, okay, and that entry will be 0 if the latest value I want, suppose I want the latest value of R4, right, if it is there in the register, then that entry will be 0. If it is currently computed, getting computed by some element, for example, I just add R4, R2, R3 and that add is executing in execution unit 3, right. So in the R4 entry, the entry corresponding to R4, I will have the value 3. So the CPU will know when it is trying to dispatch that instruction for execution, it will know for each operand, each register operand, where is that latest value. Is it there in the register itself, then you go and fetch it. If it is not there in the register and it is currently being computed by some unit, then I know which unit has the latest value. Okay, are you able to follow? So that is the register status indicator. After assuming you have followed this, let me read out that magenta statement down. Register status indicator indicates whether the latest value of the register is in the reg file or currently being computed by some execution unit, and if the latter, that is if it is computed by some execution unit, it actually states the execution unit number, it actually stores the execution unit number. Now if all the operands are available, right, then the operation can proceed. If some of the operands are not available, then the operation has to wait. And where will it wait? It will wait in the reservation station. So I had add R2, R3, R4. R3 is not in the register file, it is being computed by execution unit 4, that I will know in the register status indicator. So I know that in add R2, R3, R4, R3 value is not available to me, it is currently being computed, right. So that instruction, it is an add instruction, it can execute on one of these execution units, say 1. So it will come there and it will wait in this reservation station. It will be waiting for whom? Waiting for that R3, right. I am going to give an example for this, okay, a very full blown example for this, but you please understand what is going to happen here. So, let me read this green statement. If all operands are available, then the operation proceeds in the allocated execution unit. Add, I go and allocate it to execution unit 1 and say go and add, use that execution 1 to do that unit to do that addition. So, I start doing that addition provided all the operands are available. If one of the operand or two of the operands are not available, then what I do, I wait in the reservation station. I am waiting there for what? The operands to become available. Now, where are the operands? If the operands are not available, where are the operands? They are currently being computed by one of these execution units, right, and I know which execution unit is actually computing my operand. How will I know that? The register status indicator will tell me, right. Add R2, R3, R4, R3 is some 6 means execution unit 6 is basically computing the value of R3. So, you wait till the 6th fellow finish, right. So, I know that. So, I will come here to the reservation station and wait for the 6th fellow to finish, right. Now, so when the 6th fellow finishes, I put till 4, let us assume till 6, he will write the result in this common data bus. He will not only write the result, but he will also write the unit number. That result will go to the register file or memory depending upon whether it is a store instruction. Store instruction means it has to go to memory. Other instructions, this is a load store architecture, other instructions I have to write back to register. So, that data will go to the register file and the same data will be fed back to all these reservation units. So, as the data is moving from the ALU to the register, the data will be fed back through this violet line, it will also come and fed back into the reservation station. So, if I am waiting for execution unit 6 to finish, I will be pinging this, right, you have all done ping, right, have you all done executed ping, right, have you executed the command ping? Yes, yes or no? No, okay, go and so find what is ping. So, it will basically find out whether an IP address is alive or not. So, you send some packets in the network to find out whether an IP address is alive or not, like. So, I will be watching eagerly the common data bus, and if the and what will happen if 6, he will write the result and he will also put the unit number. So, I will be just watching for the unit number 6, 6, 6, 6 has come. So, I will grab it and I will start executing. So, the result did not go to the register file and then come to me. As it was going to the register file, it also came and dropped into my execution unit. So, this is operand forwarding. Followed? Really? Okay. Now, every execution unit writes the result along with the unit number onto the common data bus, which is forwarded to all reservation station through this violet bus and also to the register file /memory. So, if I am waiting for a result, that result will come to me when I am waiting through the violet bus. Able to follow? Right? Now, now we will go on to an animation, we will just spend 10 minutes, 9:55 I will leave you. Okay. So, to sum up, there is an instruction fetch unit. The instruction fetch unit will fetch multiple instructions, decode them. Then there is a register status indicator which tells where is the latest value of the register license. Is it in the register itself or is it being currently computed by some execution unit? So, when I am proceeding to my computation, I will know for sure whether the data is already available or I should wait. If I need to wait, I go and wait in the reservation station, and every unit when it finishes, it puts its unit number and also the result, and I know from which unit my result is going to come, and I am waiting there. So when that unit actually dumps the result on the common data bus, it will come to me through the violet bus and I will take it and start proceeding. So operand forwarding is happening and automatically your instruction gets stalled if there is a data that is currently being computed and it is not available to you. Both of the things are happening. When there is a data which is currently getting computed by a previous instruction which I need, automatically I am stalled, and when it completes, the data gets forwarded to me automatically. Are you able to understand this architecture? It's very simple, very nice architecture.